Yeah, so welcome everybody. I'm Disconnected. And I'm going to talk about Pwndbg, which is a plugin for GDB and LLDB for low-level debugging or exploit development. Few words about me. So I'm working as a staff security engineer at a company called Trail of Bits. I'm working on auditing or pen testing software in a application security field. So basically, I'm looking for vulnerabilities in different kind of software, not necessarily low-level ones, but as well, sometimes it's even Python or some higher-level languages. I also play capture the flag security competitions, and those are cybersecurity competitions where sometimes the tool that I'm going to show you, Pwndbg, is used for exploit development or some reverse engineering. And well, I'm maintaining this tool since 7 years or probably longer. It's on GitHub, yeah. As I said, it's on GitHub. We also have GitHub sponsors. If you want to help us, you can contribute. It's on MIT license as well. And as I said, it's a plugin for GDB and LLDB. It's written in Python because you can script both of those with Python. And well, as I said, it helps with low-level debugging, which we'll see in a moment. This can be useful, for example, when you're debugging some embedded devices or software, because well, in there, you may not necessarily have source code level debugging, and even if you have, you may need to look deep into the assembly level or the CPU instructions, what's going on. It can also be helpful during debugging of JIT compilers or JIT systems, basically. So, well, I guess it could be helpful debugging the JIT subsystem in CPython. And obviously, it's also helpful for some security research, reverse engineering, or maybe exploit development. And for those who do not know, exploits are small programs, well, not necessarily small, but programs or scripts that leverage some vulnerabilities in software. And people develop those. Some people develop those for a living, basically to maybe exploit your web browser. So you, for example, get a link on, I don't know, Signal or some other messenger. You go to the website, and there is maybe some JavaScript code that tries to exploit your web browser to hijack your phone in the end. And it's very non-trivial to develop those because, well, software is getting more and more secure with time, right? I mean, not necessarily with time, but we as a society are kind of better in developing more secure systems. And also we develop more secure technologies like Rust, for example, right? Yeah, a few statistics about Pwndbg. Well, it has almost 9,000 stars on GitHub. I have no idea how truthful those statistics are, but more and more people use that. It has lots of forks, lots of contributors, and lots of files. And interestingly, we also had a day where we had more than 100 commits. I didn't really looked up what, or maybe that was a week, sorry. I didn't really look what we did back then, but yeah, I think it's a pretty good statistic. Yeah, so why do we exactly need it? I told you some of the use cases there, but usually when you are developing some software, I don't know, we will have some kind of main C file, which is written in C language. We look at some C language here today, and assembly as well. And if we would compile it with a compiler, well, you can obviously run it, and it will, well, say hello world, right? Then normally you would use some VS Code or maybe Visual Studio or C Lion, and you could, well, debug it line by line in your IDE. But you can also, well, reverse engineer this software using tools like IDA Pro or Ghidra. Those are disassemblers available out there. Some are paid, of course, like IDA, for example. And you can look up on this binary file that we have, and you can analyze it. Well, what kind of instructions does it have under the hood? We need to wait a few seconds just so that this analysis goes on. For some reason on Linux it hangs for a second. But when this finishes, hopefully soon, should be faster. I'm not sure why it takes so long. Yeah, demo gods, right? Oh yeah, yeah. So we are here. We can see the main function that the disassembler figured out. Actually, well, in this case, since I compiled it without any optimizations, and without any stripping of the binary information, there is some metadata included in the binary. So for example, function names are included there. This means that also the binary file is bigger and it's much easier to analyze it. So for example, when you get, I don't know, a game installed from Steam and you try to analyze it like that, you won't see the function names because they probably stripped them. to make it harder for analysis. This tool can also decompile the code, so change the assembly code that we saw, the assembly, the thing that the CPU understands, and it can show you how a pseudocode like C would look like. It's not necessarily correct because, for example, this hello function doesn't really take 3 arguments, but it thought so. So that's why it showed like that. And we can jump over it, and we can also rename names here. Yeah, so those tools are kind of powerful and can allow you to refactor the code on the fly when you're analyzing something. And in this particular example, it's very trivial, but I will show you later that it may be much, much harder. Normally you would have some kind of IDE. You could debug things line by line through the source code. But maybe if you don't have the source code, well, you would probably go and launch something like, no, okay. Can I kill it? Yeah, okay. You would probably launch something like GDB on it. Oh, is it like that? No, I don't want any debugging information for that. Especially that it's my binary, so that wouldn't be any. And you have this kind of raw interface here, like a console one, so you can break on a function, you can start the program. It stopped there, and well, you can see that it stopped in main on some address, and well, what else can you do? You can inspect, for example, the CPU registers, and you can see their values here in hexadecimal, here in decimal. You can inspect, for example, some of the source code that is there. So using some GDB fancy commands, you can see, well, this X stands for examine memory. And you can see some CPU instructions out there disassembled by GDB. This debugger, right? And you can also navigate through it. So you can do something like next instruction, and it will jump to the next instruction, but it doesn't show it. By default, you can make it so that it's shown, and that's also what we do in Pwndbg. So now if I retry this with Pwndbg, so without this flag that disables it, and run it again and break on main function, you can see there is plenty of information being displayed here. Yeah, so there is some kind of context of information that is displayed to you every time you stop somewhere in the program. And this is very helpful because, well, you immediately know more or less what's the state of the CPU registers. You know where you are in the disassembly or assembly code. You know what's the memory of the stack of the program. You know where you are in the program through the backtrace at the very end. Yeah, and well, maybe we'll go to this later. But basically, maybe we can do it now. So why would you care? As I said, you may have those vulnerabilities, right, that can be very painful. But to think about it, I prepared some kind of very simple example. It may not be super trivial, but basically we have this structure here that we will have it in memory. It has 8 numbers, each is of 1 byte long, and it has some function pointer. Well, this function pointer can be assigned to anything, and then if you call this function pointer, you call the function it points to, right? We instantiate this here, the structure, object of the structure, and we point it to the function hello. Then we just randomize some numbers, 8 of them, and then we call this hello function here. Maybe do a get car here so that the program will stop. And it will compile it now and run it. It will say hello world, right? Because the hello function was executed. We also have some win function here. This win function, it's being declared here, but it's actually never ever used within this program. Well, actually, I print its address here just for the sake of making it easier. But basically, I'm not using this function anywhere further. So now, if I press enter to continue this program, it will print me some of those function addresses, and it will print me the numbers that it randomized. It doesn't really matter. What matters next is that we have this functionality here that we can provide an index and a value, which number we want to modify. And we don't really make any check whether we go out of bounds. In Python, if you would have an array like this, and you try to assign to its 100th item some value, you will get an index error. Something like this does not exist in C or C++, unless you implement it. If you do something like this in C or C++, I mean, something similar, like here, we do, well, you just modify some value in memory at some address, which, it may be a different variable that the one that you were intended to modify. Let me modify the program back because it made it a bit harder to show me what I wanted to show. But if I rerun it now, it will do the same, but just without stopping at the very first item. So now it tells us provide index of number to modify and a new value. So if we provide index 0 with a value of 1, it actually modified the numbers 0, right? Doesn't really matter. It's like the program succeeded. And at the very end, we also call the function pointer again. Since the function pointer was initially assigned to hello, the hello world is also printed out. But if we rerun it, and now instead of modifying an item of this array that was within the array, we try to modify an index out of bounds of this array, like index 8. There are 8 items, so the last index is 7, right? So we try to modify the index 8 with, for example, value of this E3 byte that is here, which I don't remember how much is this in decimal, 227. If I do this now, well, we modified the numbers and the 8 index there with this value, and now instead of hello world, the win function was called. And this is all because we kind of corrupted the memory of the program in an unintended way. And so we never called this win function in the program, but we called the function pointer, which we modified in this process. And this is very trivial and a baby example, right? But you may have very complex programs like web browsers or operating systems or basebands in your mobile phones that may have similar vulnerabilities. And of course, well, maybe they try to do the bounce checks, but maybe they do it incorrectly. Maybe there are some compiler optimizations. Maybe the JIT compiler optimizations are made incorrectly, like some assumptions are made incorrectly, and maybe some checks are removed by the JIT compiler incorrectly. And those cases happen from time to time, and people exploit those. And as you can see, we kind of exploited it here to just call the win function. But if you think about it, we can actually, jump anywhere in the program. We don't really have to jump to the win function. We can, for example, call main again here. Like if I rerun it and modify the 8th index with the fd value, which is 253, the program just restarted itself because instead of calling the hello or the win, we called main again. So yeah, we came back to the same place now. And well, if I would try to modify, for example, some random index with some random value, the program may just crash because we corrupted something that the program wanted to use, and maybe it jumped in some incorrect place in memory, and well, it was not the correct instruction. So those things can also happen, and if you get a seg fault, that probably means that there is something not well going on in your program. And you may think that those vulnerabilities would never exist in something like CPython, but well, CPython is written in C, so it can also exist. Some things like that can also exist there. But even if you are writing just pure Python code, you also have modules written in C, which also may have bugs like that, and sometimes have bugs like that. And whether a particular bug or vulnerability can be exploited really depends on the case-by-case basis, because well, it all depends how all of this would be compiled in the end, and what would be the resulting assembly, what would be the memory layout. So this thing may differ between operating systems, between architectures, between builds, because well, if I add here get car here and recompile this and rerun this, we can see that actually now to go from hello function to main function, we would have to modify 2 bytes because there is this E2 here and E1 here, right? So hello, and the address of hello ends with E1, E9, and main and win ends with E2 something something, right? So we'd have to modify 2 bytes. So now we would need to have some kind of exploit primitive to write 2 bytes instead of 1 in order to, well, call one of those. Interestingly, on on a lot of architecture, well, on x86 or x64 architecture, the ones that we usually have in our desktops, not mobile phones because that's ARM, and not the Apple Silicon MacBooks. Well, if you have an assembly instruction, and this assembly instruction has, for example, I don't know, 4 or 6 bytes in memory, you can jump in between. I mean, you can jump into like in the middle of this instruction, in the middle of those bytes, and the CPU will just happily interpret whatever bytes are there and execute whatever instruction those new from the middle bytes disassemble to, which is pretty, well, not great if you think about it, because this now means that for a lot of instructions that you have normally in the program, in an intended way, you also have some kind of sub-programs in your program due to the fact that you can jump, well, in between instructions. Because different instructions have different length of bytes, so, yeah. Oh, and by the way, for this specific program, we can also, analyze it with tools like IDA or Ghidra. And you can then check up the layout of the memory that is there in the program, which we need to wait a few seconds for that. Obviously, great Linux, and it's, well, the tool may also not be great written since, well, it shouldn't hang its main thread, I guess. Yeah. Yeah, so, this here is a bit more complex now. We can see the branches here that, there are some if conditions here and there. We can see some call to the functions like printf, right? We can see some comments that, hey, here's the format string literal for it, and so on. But interestingly, because also see here those variables here, and those variables here tell us like what's the, or if we like click on it, what's the kind of layout on the stack memory here. And we don't have names of the variables here, but we can also decompile it. By the way, I probably need to connect my battery. Sorry. 1 sec. Yeah, but you can see, by the way, the pseudocode here now, which is not exactly the same as the C code because we don't have the variable names except of the function names. Yeah, back again here. Does it work? Yeah, it works. Yeah, and as I said, you can refactor stuff here. So for example, we knew that we had this function pointer that points to hello here, and we knew we had some kind of numbers array. So for example, we can rename this to function and then know where it lies here in this well, memory. And yeah, here are probably those numbers somewhere around here, or maybe even earlier. Yeah. Yeah, so let's now talk about some of the features of Pwndbg that are helpful here. So as I said, we have some context that's being displayed. Now we look into what's exactly there. You can, by the way, also display context by using just a command called context. Well, it starts with some legend, because as you could see, we have some colors here and there. Like sometimes there's some red, sometimes there's some blue or yellow. So whenever we know what's the memory that the value points to, or the address points to, we color it with the corresponding color. So for example, if we know that something is like the stack memory of the program, we color it in yellow. If we know it's heap, then in blue. If we know it's some executable thing, then like executable memory, we color it in red, and so on. Then you have this whole lots of different sections, and this can be configured to display like less of them or more of them. There are some other optional sections that are usually not displayed by default as well, like for example the threads that are there in the program, because like when you're debugging a program that has just one thread, then maybe you don't really want to display it by default, right? Yeah, so we start with registers, and as you can see, all those values that are displayed are automatically like telescoped, which I will maybe explain in a moment. But basically, first of all, we color the values, and then if there is some symbol, we show you the symbol. And then if this is a pointer to something, we show you where it points to and what's in there. That's why it may be a bit, bloated how it looks like, because like there is lots of information displayed here, right? Then we have disassembly, so basically the CPU instructions that are out there. We may have source code, like you may actually debug with source code, right? So if you have the source code, you can have it here as well. We have the stack memory content. So we just display part of the memory that the program usually uses, because stack is usually used a lot by the programs. And backtrace, so like where you are located in the program. And as I said, everything is telescoped, which means we try to dereference any pointer that we see there. So if you have like a pointer to int, like pointer, 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 pointer to pointer to pointer to pointer, we dereference it and so on and so on. And to give you an example, we may have a structure like error with 3 fields, like message code and some callback function pointer. And if you would instantiate it like that in a program, so you create an object of error, and then you create a pointer to this object in the program, then if you would do something like telescope on this pointer here, on the address of the pointer variable, which means that this is the address of the pointer variable, and then you can see this, since we assigned it to the address of the E object, this will be the address of the E object, which interestingly is just afterwards in the memory. And then you can see the whole error object in here, which it is not maybe so obvious that this is the error object, but it is actually the error object. And if you look how it was like instantiated, the very first member of it, so the pointer to message was div by 0. So for example, here we have this address which under the hood, it has this div by 0 string in there. And for example, this 0x1 that was assigned in the code integer, you can see here it's also there, and the same for the puts function that was there. So you can figure out a lot of stuff like this in memory thanks to telescoping everything. We also have some kind of smart disassembly, because when I showed you in this GDB session, like if we do some break, blah, 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 and maybe we disable any context here. So for example, if you would normally disassemble some code in GDB, you would see it like that. And well, this is useful because, well, you see the instructions that are out there. But it may not show you everything that may be useful. So first of all, we display function arguments. Well, there are lots of known functions that are out there. For example, system calls on Linux, like this write function here. And you can inspect its documentation with manual on Linux. So if you do that, you can see the description of it, like write the file descriptor, right? But what more interesting, you have the name of the arguments. So the first one is, for example, FD, which stands for file descriptor you want to write to. And, well, we display it for you. So whenever you are on a call instruction, or even before that, usually, we will display you the values that will be there for this call, which I guess is very helpful. We also have nonlinear disassembly. Well, since you may have branches, I closed IDA Pro, but you may have branches in your code. Like, you may have an if condition so that you either go to the left or the right, depending on the result of the comparison. This is usually realized by some jump if something instructions in assembly. So for example, here we have this JE instruction, which stands for jump if equal. So you can think of it like if 2 values that were compared are equal, then we will jump to the address that is, well, the operand of the instruction. In practice, all the jump instructions are somehow related to some flags in the CPU, because like any kind of comparison instruction or even subtractions set some flags in the CPU. And so, for example, this GE is checking the ZFs or 0 flag in the flags register of the CPU. And here you can see we have like a linear disassembly. So each of the instructions that you see next is like the next instruction in the resulting code. But in practice, if the program would go to this jump, I mean, if we would execute this jump, then maybe you don't want to see what are the instructions afterwards. Maybe instead of this instruction, you would like to see the instruction that you would actually go to. And this is what we do. We actually figure out whether a jump is taken or not, and we will display you the very next instruction that we will jump to. And we also predict values, both statically and also by emulating code. And that's also how we know whether a jump is taken or not, by the way. And so, for example, here you can see those instructions on the left side, but on the right side you can see a lot of, I would say, a bit bloat, but basically those are the values of the CPU registers and sometimes memory that will be set by the instructions on the left. And our program is stopped on the very first instruction of this function. So we can see what will be the state of how the state of the process will change throughout those instructions. This may obviously not be so true always, because if you would have a multi-threaded program, well, another thread may change some state under the hood in the meanwhile, right? So, there are some cases where this may not be true, but yeah. And well, how do we do that? We use two frameworks that have like Python bindings. There is Capstone and Unicorn Engine. Well, Capstone is a disassembly framework. It supports a lot of different architectures and well, can be used in Python. And Unicorn is well a CPU emulator. So how do we emulate code? Well, we have a code that looks like this. So we kind of have some kind of emulator object under the hood. We map some memory into the emulator, and then we copy memory from the program that you are debugging into the emulator. We copy the code into there, we copy the state of the registers, and then we execute like some of the instructions, and then we look up the state, what will be there. Which may be heavy. That's why you can actually disable emulations as well, because sometimes reading memory when debugging may be well, expensive. For example, if you're debugging some embedded device. Well, and we have plenty of different other features as well. Well, one kind of painful thing in like GDB or LLDB is like navigating through code. Well, if you don't have like source code level debugging like in IDE, which you may have with GDB, because well, GDB is used within CLion or VS Code or some other places or LLDB. But if you don't have this, well, you can only refer to some of the commands that are there in GDB. Like, you can set a breakpoint in main function, and you can, or maybe some address, and you can continue the process and see when it stops, right? You can also do something like step or step I for stepping into. Why does it clear? Okay, I don't know why. You can do something like step I for stepping over into next instructions and also into calls. Or next I to, well, go into next instruction, but like go over calls. So if there's like a call of a function, this function will be executed, and the debugger will stop on the very next instruction after the call. There is some finish and until that usually works only with source code, but we add a few more out there. So if we were to rerun this, well, first of all, there is something like syscalls on Linux. So there are like functions that you execute when you want to like ask the system to do something, like write to a file or to a file descriptor or read, networking, and plenty of other stuff. So for example, you can do step syscall here, and it will basically step over each instruction one by one and wait until a syscall instruction is hit. And the output of this is painful because, well, this is some output that is printed by GDB, which we cannot truncate. But as you can see, we now stopped on this syscall like fstat, which is checking some statistics of a file out there. And well, we also display the arguments here, as you can see. If I retry this, we can see the next syscall that is executed, and so on and so forth if I continue, right? So this may sometimes be helpful. Also, if you want to like wait until this function finishes, and functions usually like exit through ret instruction, you can do something like step ret. So step until a ret instruction is hit, and we are on the ret instruction now. And you can see this arrow here, by the way, where you are in the code. Oh, and by the way, I didn't say that, but whenever a register changes between different points in time when you stop, you can see this like highlight here that like tells you that this particular register has changed as well. There's plenty of others. Like, for example, I don't know, if for some reason you want to step your program until, I don't know, XOR instruction is executed, you can do something like this. step until assembly, and you can provide here an assembly, like regular expression, and it will continue until an assembly instruction is executed. Why would you why do you want such a feature? Well, if you have some kind of checks in your program, like I don't know, something that checks for some code or for some secret, or maybe does some kind of encryption or decryption, well, usually XOR instructions are included, so you may wait for it. Another use case is once I debugged some kind of hypervisor. Hypervisor is like a system, well, like a program basically that runs virtual machines. And you have special instructions in CPU for running virtual machines. So if I don't know where such an instruction in the program is in there, which I could probably look up in IDA Pro maybe or Ghidra with some disassembler and some searching, I could just do step until asm and VM start, which is the name of the instruction for that. In GDB, you can actually display the memory mappings of the program with info-proc mappings. So this shows you where all the memory allocated by the program is. Well, the memory is not necessarily allocated in each case, but those are the the addresses that the program can use somehow with some specific permissions. Like this memory page is only readable; you cannot write or execute it. But for example, this one has this X bit, so it can be executed. So this one contains code. But this is not so cool to read through, and so we have a corresponding feature, but with colors. We also can search over memory, because while in GDB, the searching for memory requires you to provide start and end address, and you don't necessarily always know it, and you cannot provide 0 and some huge address. So instead, you can just do search, and I don't know, we may want to find bin sh, and it turns out that this specific string is located in the libc library on this very address here. We also have a proper hex dump, because you don't really have that in GDB. Well, you can examine memory like this and some address or register, but we don't see whether this is an ASCII character or not. And with hex dump over this address, we can see the hex dump here, which may sometimes be useful. You can configure plenty of stuff. So how many lines of code you want to see, or disassembly, or stack, whether you want emulation, and plenty of others. You can also change colors, because sometimes people want to change them. And interestingly, you can also attach the process by name. So for example, if I run Firefox here, and I rerun this with sudo, because you need to be root to attach to processes. Well, not necessarily, but here, in this case, yes. So I started Firefox in the background, but now I can actually attach to it. So if I attach to Firefox, I'm now debugging Firefox process. And I can see, for example, that it has 96 threads, and I can see the name of those threads and where are they in the program and so on. Interestingly, I can also see some kind of information about the process with the proc info command, which is here. So well, the name or the target of the binary that we run, all the file descriptors that it has opened, and then there can be anonymous Unix domain sockets, and they may be sockets, for example, to Wayland, some pipes as well. There should be some kind of TCP connections. So normally, this information you can figure out this information on Linux, through proc file system, but not such in a straightforward way. If you would look it up in proc file system, you would only see that, oh, this is a socket, but it wouldn't show you where it points to, and here we figure it out for you. So it may be cool if you want to figure out what kind of IPC mechanisms your process have, or where it connects to, and so on. I didn't say that, but usually programs, well, I showed you that you may have a bug where you have some kind of out-of-bounds write into the memory, right, with this numbers array. But sometimes you may have a bug where you just can't write from a given point in memory until well, very long length, for example, and just corrupt lots of memory. And there is this mitigation on Linux for programs, which is called stack canaries or stack cookies, where maybe I will go back here, where in the very, very stack memory that you have, you may have some kind of special value called stack canary that would be here. And this value is placed in the stack memory whenever you enter the function, and it's checked against its global value whenever you exit the function. This way, like before exiting, because the fact is that whenever the function exits with the red instruction, it knows where to go to because the return address is saved in the stack memory. So if we can change the return address, we can also jump anywhere in the process memory space to executable code, right? And so to prevent from this kind of cases, the stack canaries were introduced. So now if you corrupt the stack canary, the process checks it before exiting a function and, well, it crashes itself. And we can actually display those canaries, and I can do it here in Firefox, which will show us like a lot canaries for each thread that is there in the process. Yeah, which is maybe not so interesting for us right now, but yeah. Going back in there. You can also spray memory. And if you are doing some kind of exploit development, you sometimes want to, like if you have some kind of like buffer overflow where you actually corrupt memory, as I said, right? You may not necessarily know what's there exactly on a given address in memory, but you may want to kind of figure it out on the fly, just running the program and rerunning it with different inputs. So you can actually simulate some of this. So for example, here, if I would dump the memory of the program on the stack, you can see this is the stack of the memory. But if I would have some primitive that I can write from this address up to some other address, I can also simulate it here with something like this. So I sprayed this memory, and now you can see that, well, it was some kind of values like AAA, BAA, CAA were placed in there. And now if my program would crash, I try to continue, you can actually see that it crashed on the return instruction here. It got segmentation fault. I can see that the return tries to jump to this address. And now I can kind of decode this address and know on which kind of index from the address I was corrupting this is, and so I can now like exploit this by putting there some kind of interesting address to jump to. Yeah, there are also features for finding some kind of pointer to pointers, because like when you are developing an exploit, you may actually have some write to memory, but you want to find some interesting pointers, for example. So there are features for that as well. There is something to track, well, GOT calls, so global offset table. Global offset table is like a functionality in ELF binaries, so in like Linux processes, where if you are calling some kind of external function from an external library like glibc, this goes over this thing called global offset table, and like the addresses of the functions are saved in there. And sometimes you can corrupt those addresses so that, I don't know, instead of calling printf function, the program will call something different. And we can track it. I won't do it on Firefox because that will probably not work nicely due to threads, I guess. But if we would start here, let me do it like that. We can do something like track GOT enable, and whoa, it didn't work, I guess. But if I try to continue, okay, it crashed in this case. I'm not sure why. Maybe we broke it, and maybe we don't have a test case for this particular scenario. You can also inspect the memory allocator itself. So like glibc has its own heap, and you can inspect the heap. So for example, we have this, the heap was not initialized here, but okay. I won't show you the source code, but basically we have some program that allocates some memory, and we can inspect like the memory chunks that were there. And you can also displace those memory chunks with some kind of visualization feature. So for example, there is some kind of memory that was allocated on the heap, which has just zeros out there. It's probably allocated by glibc. And you have 3 chunks that I actually allocated with some, some values that I placed in there. And here's, for example, some memory that probably the printf function allocated just to place its buffer in there. And this can be helpful whenever you would have some bugs on the heap, so that you could maybe corrupt from this memory to this memory to this memory, because there is some metadata included in those chunks. And if you can corrupt those metadata, it can be helpful for exploitation. Yeah, we also have kernel hacking features. I won't really show that because we don't really have time. We can patch instructions. So I don't know, you want to skip a jump or a condition, you can patch it. And we have lots of more stuff out there, and people are contributing more and more. And that's basically it. We now have 5 minutes for questions. So thank you.
Thank you, Dominic, for your presentation. Do we have any questions from the audience for Dominic?
Yeah, the question is about the roadmap for next implementations. So interestingly, we take part in GSOC, which is Google Summer of Code, and PSOC, Python Summer of Code. So we have three people working on 3 different things. One is, well, actually getting more and more LLDB support, because that's it's getting more and more interesting, because, well, if you want to debug some iOS stuff, you need LLDB. Now on Android, the LLDB support is probably better as well. So we're doing that. We have a person who works on adding Musl heap allocator, because, well, you have, for those who do not know, you have glibc, the libc library from GNU, which is open source, but you have many other implementations of this libc library, and Musl is one of them. It's usually used in, I don't know, some embedded stuff maybe, or when you want something smaller than glibc. And sometimes you have programs that are, buggy that use Musl, so you want to exploit them as well, so you want to inspect this heap. And we have another person who tries to port it to Pwndbg on Windows, which is a pretty non-trivial task, considering that the interface for dealing with that is different. Yeah.
Thank you for your nice talk. I suppose you're using macOS, MacBook, but
yep.
I'm really wondering that how did you make the binary on Intel architecture and you debug
VMware. Well, this is macOS, and here is Ubuntu on VMware. So this is just, oh, and this is Intel Mac, by the way. But yeah, I have VMware, so I'm having a virtual machine with Ubuntu here. So that's why I'm dealing with ELF binaries here. Well, Pwndbg also works on macOS, but the support of it varies. Well, if you go to Pwndbg and to releases, we now have a really good kind of release, not schedule, but like way we do releases now is pretty great, because we ship it to many different architectures and operating systems and so on. So for example, here is some version that will work on Intel macOS, but it doesn't support debugging macro binaries, but remote ELF debugging, for example, instead. Yeah, but we are getting to it to get more support here as well.
On Ubuntu system, does the binary on is not like ARM architecture?
Sorry?
Is binary generated on Intel architecture or on
It's Intel, but Pwndbg can work on ARM as well. I mean, we have portable releases. So for example, this one here will work on any ARM Linux to this degree that it can actually work on an Android device, which we tested on some CTF competitions. So not necessarily always without any kind of changes, but sometimes, yeah. Sometimes some changes like in environment variables are needed because we didn't consider that something may not be set or something like that.
Okay, thank you.
You mentioned that the emulation doesn't work so well for multi-threaded programs, but I was thinking that like each thread has its own registers. So
yes.
it's not register. So is it memory or what are the limitations?
It's just our support. We don't really emulate multiple threads, because if you think about it, how would you do that in such a way that would be reproducible? I mean, that it would correspond to the actual execution. If you have multiple threads, you have some kind of scheduler that schedules them somehow. And if you would emulate that part as well, how do you know that the normal execution would not schedule the threads in a different manner? Good luck predicting that.
Yeah, but it's about showing like what the values will be, right? So
sure, but you may have two different threads that will modify the same memory.
yeah, so memory, that was ours.
Yes, memory.
Okay.
Memory is, yeah, the state of the memory is different. Also, if you think about it, not everything can be emulated, because there are some special instructions that you cannot really emulate. So in this case, we emulate up until this point of this special instruction, and then we stop.
I'm sorry, we're running out of time. So thank you all for joining us today. And thank you, Dominic, for the talk.